So he's an associate professor at University of California in Irvine, and since very recently, he is in Germany as a director of Jülich Research Center to continue and extend his really interesting and exciting research that is bridging concepts from machine learning, neuroscience, and neuromorphic engineering. So yes, so with a lot of pleasure, Emre, please.
Thank you, Malika. Can you hear me well?
Yes, we can.
Okay, great, thank you. It's a great pleasure and actually even really an honor to be the first to speak at this conference. So thank you a lot for the invitation. So the topic of today is going to be pretty broadly telling about my experience in training neuromorphic hardware and the successes that we had using differentiable programming. I'm also very glad that Jason gave his tutorial just before me, because actually in doing so, he introduced a lot of the concepts that I'll be using today. So thanks a lot, Jason, for that. So let me start again just from this figure here. So this is a cool experiment by Josh Tenenbaum that in fact he used at some point in one of his own talks, which illustrates how quickly we as humans can learn new concepts. So here, for example, if I tell you that you have these three objects, they are of the same class and I call them tufa, and I ask you to find the other tufas, you will have no trouble in finding them. So here, 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 and so on. Okay, so what you've done here is, if you've never seen these slides, this particular figure before, you've actually learned this concept or this object, the tufa, and you were able to generalize for different viewpoints and even different variations of this object. Now, how cool would it be if we can imitate this type of learning and achieve this kind of learning in our hardware? So that is one of the goals of my dreams of achieving. So this and all the capabilities that this fast learning and adaptation can bring to technology. And also, of course, in understanding how these concepts arise in the first place. So I'm going to be telling you about all the experience that I had over the last years in using differentiable programming, so the tools of machine learning in doing this. So just for the very quick reminder here, just to set the context, neuromorphic engineering is really trying to capture the brain's physical processes in a physical substrate. So what this means is that we're not merely simulating the brain's functions, but actually building a piece of hardware whose dynamics may correspond at some level to what that is happening in the brain. So the field, of course, as you may know, started with collaborations through Feynman and Carver-Mead and other researchers in the field. And I like this quote of Carver-Mead, which illustrates this idea that the constraints in a physical system are going to be similar no matter which system you look at. So in particular, silicon systems are going to have constraints similar to neural systems, whereby wire is limited, power is precious, and robustness and reliability are essential. So, and I take this comment as a way of saying, so it doesn't really matter at which point we look at this this hierarchy or these different skills. At some point, if we can match these constraints from a physical system to a computational system, we might actually be achieving something similar to the brain and vice versa. Okay, so this is really what I mean by physics of computation. And as soon as you introduce this idea of physics of computation, you also enter the problem and the issues of how do we actually communicate information. Communication itself becomes a physical process which has a cost. And that cost, when you take it together in the overall system, may actually make a system, as one that would have evolved and would have through the pressures of evolutions would have disappeared, right? So in some ways, we're trying to to capture these the concepts of neuroscience in our system to build systems that are lower power and that can function efficiently in terms of data and so power. Okay. So one of the main ideas of neuromorphic hardware is that the processes or the circuits communicate through address events. So this is one of the early figures of representing the address event representation, in which case you have here these neurons on the horizontal bars, excuse me, that emit these events that are encoded into a common bus and that decoded at the receiving end. So these events represents the action potentials. So this particular architecture has some interesting computationally and architecturally interesting features. One, which is that the neurons only output these all or none events, whereas all the other dynamics is maintained within the neuron or the synapse. Okay, so basically the input-output of this neuron is pretty efficient. So in terms of spikes, I say low amounts of information going in and out. What this also means is that a lot of the computation is going to occur in a local fashion. Okay, and locality, as you may know from different areas, may actually be a very good thing for scalability. But of course, it's challenging. It's challenging in that most of the algorithms for computation or that we can think of actually rely on some form, often rely on some form of global computation. And note that this problem is not so different than the same problems that you would get in, for example, in-memory computing, right? So in in-memory computing, you're trying to move as much as the computation as possible into the memory, but you're hoping that you're not going to have to send around too much information across the processes. Otherwise, you lose this benefit of bringing computation to the memory in the first place. So these are similar problems. So let me try to picture now the problem that we're tackling with the overall fields of machine learning, since I told you that I'll be going towards machine learning. So on the one hand, of course, we have machine learning relies on powerful software. We've seen a couple of these today with Jason's talk, PyTorch, TensorFlow, JAX, and so on. And hardware, either general purpose CPU or specialized hardware that implement these machine learning accelerators. There's now a fantastic software infrastructure allowing you to program machine learning or computational pipelines and compile them on a piece of hardware. And we've seen, as we see today, and how the models scale, this is working very well. The idea is, can we use this same infrastructure for neuromorphic computing? And of course, you've seen already this earlier today. Yes, so of course this is possible. So let's first add the box of neuroscience here. So without machine learning, typically the way neuroscience is used in this ecosystem is that we have software for simulating, say, spiking neurons or biologically plausible neurons, NEST, NENGO, and so on, and neuromorphic hardware, in which we can directly inject some of these neuroscience concepts into hardware. More recently, either in computational neuroscience or in machine learning, we've seen this exchange of ideas from machine learning to neuroscience, either using machine learning as tools for statistical analysis in neuroscience, or more interestingly, and what I'll be more focusing on, machine learning as a model of what the cortex or a piece of cortex or even just a small circuit of neurons would be doing. And there's been some a flurry of work in this direction, which allows us to directly translate neuroscience monobiological neural networks into machine learning concepts. And what this allows us is this kind of a middle out approach. We're not doing top-down or bottom-up research in this sense if we operate on this machine learning, but we're trying to find some of the basic concepts that both fit onto the underlying substrate, underlying physical substrate, which is this neuroscience or neuromorphic hardware, and the algorithms that may allow us to implement useful and solve useful problems. Okay, so, and I do mean here machine learning in the largest possible sense, right? So you can also imagine that we can use machine learning as a way of calibrating mixed signal hardware, for instance. We can also use it for deep learning networks and transferring parameters and so on. But in this talk, I would really like to make a case for using machine learning theory as a way to understanding learning in neuromorphic hardware. So luckily, I can go pretty quickly on the following slides, thanks to Jason, Jason's introduction. So I hope if you haven't seen that, I'm still going to go through these slides. If you want to have more details on neurons, I would recommend you to check out his tutorial. So the basic building block that I'll be starting about here, and as also a block for the discussion and presenting the ideas here, I'm going to start with this discretized leaky integrated fire neuron. So this is a neuron that integrates inputs as these exponential, double exponential inputs. So these are the postsynaptic potentials in response to every input spike, which every now and then produces an output spike, resets, and so on. Okay, so here this is expressed as the memory potential at time t+1 is equal to its past with a decay factor beta between 0 and 1, a number that's close to 1. Some synaptic inputs, a reset term here, and the spiking nonlinearity, in which case this neuron spikes when the membrane potential reaches 1. So now I'm going to write these equations in a graph format, and this is because this is it's a practical way of representing computations for a machine learning framework such as TensorFlow. So because we have time here, we're going to have a different state for every time step. So every box here is a different time step, is a state at a different time step, t+1, t+2, etc. And as I add these connections, I'm going to create transformations that between these states. So in this case, we have that the state S of t, which is the spiking state, is determined by the threshold of u. We have the leak state, which connects u in time. So ut+1 is a function of u of t, in this case with just a factor in beta. And we can add the synaptic connections, which goes from S in to the membrane potential. We can also add recurrent connections, in which case the spikes go back to the membrane potential. And this can be actually, the reset events can also, in this case, be subsumed inside this recurrent connection. So what we end up here is the same graph, same computational graph as that of an artificial recurrent neural network. And this is very nice because this means that we can use all the tools that have been developed for training recurrent neural network for training spiking neural networks in principle. Okay, and so these are, for instance, backpropagation through time, as well as other variants, as I'll be talking about today. So this leads to the overall framework, which is, I think, a very powerful framework for programming neuromorphic hardware, in which we first can define, just like we do in machine learning, right? So you first define some objective function, something that if you optimize this function, you'll be doing a good job at a given task, such as recognition, navigation, and so on. This objective function is going to depend on a network in which there's a neuron model. In this case, we're going to use this leak integrated fire neuron as a neuron model, just as one as I've shown you earlier. We're going to take, as I'll be really briefly explaining, a differentiable variant of this neuron. And ultimately, the learning rule is going to be based on gradient descent, which now, given the objective function of the neural model, which is differentiable, we can compute. We just take the gradients of the loss function. Now, as I'll be explaining a little bit more later, this gradient descent rule is really interesting by the fact that it actually breaks down into multiple factors, which actually fit nicely with the biology. So, in the fact that we have plasticity is often viewed as the effects of the presynaptic, postsynaptic neurons, so a Hebbian term, as well as some modulation. But it also tells us from a hardware perspective, what are the class of functions we need to implement in our plasticity processor, whether it's on chip or off chip, in order to train this neural model effectively. Okay, so it gives you both the guidelines for designing better hardware, but also insights into how synaptic plasticity works in the brain. Okay, so of course there are certain challenges in applying gradient descent in spiking neurons. And the first one you may have heard from in the previous talk today, which is that, so this here is the loss function. So we take the gradient with respect to W and we end up with these three terms, as I mentioned earlier. So one of them is going to be reflecting how the output of the neuron changes the loss function. One, which is how a change in the membrane potential is going to change the output of that neuron. And the final term is how a weight is going to change the membrane potential. So we have this problem, firstly, that this term here is actually non-differentiable, right? So in this case, what we can do is, for the purposes of optimization, we can make this function continuous, so differentiable, such that we can now take its derivative. Now, this is an approximation, okay? Because we're using a different graph to compute the gradients than the actual gradient graph, we're going to get approximate gradients. But there's been a lot of empirical work in showing that this is indeed a valid, actually works very well in practice. And also, you can understand this as a way of starting with a very smooth a smooth nonlinearity and gradually increasing it, the sharpness of that nonlinearity. And those ideas are actually discussed in this nice paper of Friedemann Zenke and Tim Velkos. So that's all I'm going to talk about in terms of surrogate gradients, because I think that's a minor challenge compared to some of the other challenges that I'll be discussing about. One of them is the temporal credit assignment. So it's a question of how is the objective function going to change based on inputs that and states that occurred in the past. Okay, this requires maintaining some memory of the past in terms of the gradients, it turns out, in order to compute this term. If you want to do this exactly, then we have to do backpropagation through time, which can be costly, or another variant of this, which is real-time recurrent learning, as I'll be explaining, which is equally costly. So the solution to this is some sort of mixed auto differentiation, which I'll be talking about. Another issue here is the deep spatial credit assignment. In the same way that we need to assign credit in time, we need to assign credit in space. So the hidden neurons in the network are going to affect the output, and we need to understand, assign credit into a change that's made in the hidden neurons. So the solution here is to construct these approximate learning channels. And a big problem with, of course, any of this learning, especially if you're doing this in real time, is data inefficiency. If you want to train these networks on, say, on chip on the physical substrate, you're limited actually learning at one sample at a time, so as if you had a batch size equal to 1. And this can take a very long time, and you get all sorts of problems related to catastrophic forgetting. And I'm going to be talking about one potential solution to this, which is meta-learning, hence the title meta-training spiking neural networks. So let me just start with the first part, which is that temporal credit assignment problem. And just briefly, I'd like to go through the concepts of auto differentiation. I know that many of you may be familiar with this because many of you have already trained spiking or just plain neural networks in your life. So what you do is you can define your network as a composition of differentiable operators. This can be as simple as just calling this backward function, which then backpropagates the gradients from this scalar loss function in this case. So I'd like to really see this auto differentiation libraries. It is really a hidden figure of the success of deep neural networks. And I think there's a lot to be learned in how we can more effectively do auto differentiation to improve learning in our systems, as I'll be talking about here. And I'd like in particular to focus on one variant of auto differentiation. So take now, for example, let's say we take the gradient of some loss function L. Which is a composition of functions f of g. You can see these functions as being, for example, the transformations produced by a hidden layer in a network. This, as you know, by the chain rule, results in this product of Jacobian matrices, at least in discrete time. In this case, that we will have a product of matrices. As you have a product of matrices, you have the liberty of doing this product from left to right, or doing it from right to left, right? And it turns out that this choice actually affects the computational cost of doing the operation, but it does not affect the results, right? So you know that if you multiply A, B, and C, that's the same thing as multiplying C, B, and A. So if you do it in this case of left to right mode, this is often called in the field of auto differentiation. This is called the reverse mode auto differentiation. And in the neural networks field, this is the same as doing backpropagation. In neural networks, this is equivalent to doing backpropagation through time. So what happens if we do this in the other direction? So we start from the right and then we go left. So this is called the forward mode auto differentiation. And one example of this in recurrent neural networks is the real-time recurrent learning. So this is actually a learning rule that was discovered already more than 20 years ago. Actually, I think this citation is even incorrect. It should be an earlier one. So it's been around for a while. And the reason for us generally using reverse mode, so backpropagation, is because it's much cheaper to use it if the loss function is a scalar, which is generally the case. However, there's a problem with reverse mode auto differentiation, and Jason also referred to this a little bit earlier. It is that the memory increases with the program depth, in this case, time. So the longer your sequence is, the longer your memory, the larger your memory requirement is going to be. And that's not great. So if we have long sequences and we have dynamics that span several timescales, this is not going to scale very well. However, forward mode is also by itself not very scalable. I'm going to give you here an overview of what these two methods results in a recurrent neural network. So in this case, in the reverse auto differentiation case, and backpropagation through time, so we have that the errors are backpropagated through the network in time, such that after every time an input is presented, we're going to have a gradient after one forward and one backward pass, hence this t+5 here. So after 5 steps here, we will end up getting a gradient for this term. Real-time recurrent learning, instead of backpropagating the errors backward, propagates all the information necessary for computing the gradients forward. Okay, so what this means is that as soon as this loss function occurs, at that point in time, the gradients can be calculated. So it has the advantage here that it can learn all online or in real time. Okay, so that's why this learning rule is called real-time recurrent learning. However, as I mentioned earlier, so reverse mode AD, although it scales with time, the real-time recurrent learning scales very poorly with the number of neurons. You need k to the 4, where k is the number of neurons, k to the 4 operations in order to do one update. And similarly in space, we also pay basically a factor k² compared to the backpropagation through time. That said, well, we don't have the problems of the transpose, of requiring symmetric transposes. I'll come back to that later. And we can do learning online. In both cases, unfortunately, the learning is non-local in the sense that any process here must know must keep a memory of the past and also have the symmetric transpose of the weights. So there's actually a really nice way of combining reverse mode and forward mode auto-differentiation simply by doing reverse mode in space, but forward mode in time. Okay, so what this means is that all the information necessary for computing the gradients are propagated forward in time from one step to another. But as we backpropagate the errors within a given time step, we can backpropagate them. As we calculate the gradients within the time step, we backpropagate them space-wise using reverse mode auto-differentiation. This is why it's called mixed mode auto differentiation. And this is how we actually implemented our learning framework DECOL, so deep continuous local learning. And I'm also suspecting this is how Jason implemented his forward mode propagation. The nice thing of this, the nice feature of this approach is that we pay a smaller price in computation, so the time complexity reduces to k², and space complexity reduces, depending on which neural model you have, to k or k². And this is a huge benefit compared to not only real-time recurrent learning, but if you're in this linear case, it's a huge benefit to backpropagation through time. So the learning is much faster. Plus, this is a fully online learning rule, just like real-time recurrent learning. And it turns out that using some tricks that we use in the backpropagation, the reverse mode AD, it's actually local. Okay. So that's, and the sparse Jacobian part is, unfortunately, I have to skip a little bit this, but there is also one approximation in this network such that these Jacobians remain sparse, and hence we can get this advantage in space complexity. Okay, so that's for temporal credit assignments. And now we have the deep spatial credit assignments. So the problem of learning in a deep network, now just forget about time for a second, is that, as I mentioned earlier, we need to calculate how the error made by a hidden neuron is going to affect the loss function and to backpropagate that error from one layer to another. So this is like, this is exactly the gradient backpropagation algorithm. And it's a little bit like the game of telephone. So you might know this. This is a child's game where you there's a chain of people, and then you pass a message from one. You whisper a message from one person's ear, who whispers it to another person, and so on. And so backpropagation is a little bit like this first person saying no, so a piece of information, and the goal of the last person is to learn what this person is saying, but first going through this chain of people. And because as the game goes, this message gets transformed, the output is incorrect. So what's going to happen here is that this person can then say, oh, this is what I heard, and that information can go back to the sender. And then this first person can maybe adjust its or every person in this chain may adjust the way that it's going to repeat that message. This is how I teach actually backpropagation in my class. It's a fun experience. It worked to some extent. I would recommend it. So you can see that the problem here is that when you learn, so you have to have that this person knows something, or this person knows something about what has been whispered into the ear of this person. So there's an exchange of information that has to occur there, okay? Or they are the same person. Another issue is that as information goes forward and backward, well, that takes time, right? So you have to wait until the information goes all the way to the last person and then backwards in order to make an update. So that's called the update locking problem. And so all of these issues kind of hinder the implementation of backpropagation, or at least as a good model of learning in biological neural networks. So there was some attempts to solve this problem. So one you might be aware of is called the feedback alignment, where I should say this first, that in backpropagation, the story that I told you with the telephone game actually translates into the fact that the neurons need to have the symmetric transpose of the weights. And this is, in general, a problem that imposes non-locality, right? So Y1 needs to know the weights of Y2 and vice versa. And this is, by the way, biologically not plausible either. So one way to overcome this is, instead of having a symmetric transpose, is to backpropagate these errors through a random matrix, which works well to some extent. That's called the feedback alignment approach. Another variant of this is called the direct feedback alignment, where instead of backpropagating the error from layer to layer, you just directly broadcast the errors to every layer by first transforming them through a random matrix. And this also works fairly well on small problems. It turns out that a more general, or at least a better functioning approach, is to introduce this idea of local errors. Rather than having one global loss function, this network is going to have multiple loss functions for every population, or in this case, every layer of neurons. The advantage here being that there is no more backpropagation, right? So this last layer, if it's linear, in fact, does not require a symmetric transpose. Okay? So this is, in this case, or it may require symmetric transpose, but because this layer, this transformation is not learning, we don't need to constantly update the weights. In any case, it makes the learning much more local, in the sense also in time, in that we don't need to maintain information, gradient information for future use. Okay, so the immediate question that comes after, when we talk about local loss functions, is, well, we're just pushed this problem of learning into another domain, which is finding what this local loss function is. So another way to ask this, the question here is to say, so which local loss function can we assign in order to reduce the global loss, which is what we're caring about. So in our earlier work, we tried these ideas of local classifiers. So this falls into the category of labeled learning. If you have a standard labeled data set, then you can use this. So we have that every local loss function here is just a random classifier. So it classifies through a random projection, but it classifies the same labels as in the data. Okay, so that's what I mean by local classifier. So this idea is also sometimes called greedy supervised learning. And it works well, at least in some small neural networks. And this has been quantified in artificial neural networks and also in spiky neural networks now in our work. The same idea can be applied using clustering methods. So if two inputs are part of the same class, you would hope that some projection of them would cluster in a latent space. Okay, so that was a recent idea that was proposed in about the same time. So what about unlabeled learning? So labeled learning works fairly fine. So this is more of a exploratory field for the moment, but there's a lot of activity occurring in unlabeled learning. So again, so the question here is, how can we assign a local loss function to each of these layers if we don't have labels? Okay. So one approach is to use predictive coding. So, and by the way, I don't mean here as an exhaustive list of what we can do here, but predictive coding is certainly one way to do this. In predictive coding, rather than backpropagating the errors from layer to layer, you learn the error that's been made in a local layer, and then you propagate back more like quantities that are more like targets rather than errors. And this is really a little bit like this idea. corresponds to this idea of having local losses and local targets. So Nick Alonso, one of my graduate students, will be presenting this just later today. Especially, he'll be talking about how we can implement a key element of predictive coding, which is the calculation of errors in this network. A related method to predictive coding, which is also compatible with local losses, is contrastive learning. Contrastive learning actually is a very popular field nowadays in machine learning, in which I provided here 2 examples. What you do is that if you have time going from left to right here, and you have a piece of data, for example, your sample or your output, you try to predict, for example, an occluded part of your image, okay? And not only you try to predict, your loss function is in predicting that error, but it's also in rejecting or learning in a contrastive way to noise data. So data that has nothing to do with this valid part of the data here. You can do the same thing in time. So you can be, this basically corresponds to this idea of predicting the future. So if you can predict the future correctly, and not only predict correctly, but also understand that or distinguish between fake data and true data, you can do a good job in learning. And so there's been a lot of work that's been done here in the more traditional conventional neural networks, but also in spiking neural networks from the group of Gaston and Guillaume Bellec. And this moves more toward the reinforcement learning, but it's also very interesting to think of intrinsic motivation as a way of doing local losses. I mean, our brain has many different nuclei which respond to different features of the environment, also features from our own bodies. We get hungry or we have emotions and so on. You can all see these different signals as being local functions that that a neural network may optimize. And some of these ideas were actually applied by the DeepMind group in this using auxiliary tasks in model-free reinforcement learning. So if you would like to remember anything from this, is that we are not limited in the number of local loss functions that we can explore in order to implement in order to solve this problem of spatial credit assignment and neuromorphic hardware. And in fact, I think it's a very interesting and fruitful field of study. I would recommend you to look into it if you're interested. And with this said, I'd like to dispel one point, and I hope that this will bring in some discussion later on, which is that, well, if we're building hardware and we're implementing gradient backpropagation anyway, aren't we just fooling ourselves and being misguided by the fact that backpropagation is optimal? And in fact, it is. So there's been studies that backpropagation, this is a quote from Pierre Baldi's paper, saying that backpropagation is optimal in the space of learning algorithms, in the sense that it achieves the maximal transmission rate. By transmission rate is how much information you need to transmit from one layer to another versus the expected improvement. So this is true. Okay, so if you don't care about the hardware that's implementing your learning algorithm, in fact, you should implement backpropagation, and end of discussion. However, if you take energy into account, I would argue, and this is not only a blank argument. Actually, we've seen this every time we've measured energy versus expected improvement or accuracy, that there is a benefit in using algorithms that are not exact, that are approximations of backpropagation. And roughly, this a rule of thumb here is that you would need approximately the same number of synaptic operations, synaptic operation being the equivalent of a multiply accumulate in a conventional processor, but in neuromorphic hardware, to achieve a given accuracy. Okay, given that a synaptic operation is generally, at least it's potentially a sparse operation, and it's a multiplication with a variable that has a single bit, basically just reading from a memory, this can be much cheaper than the multiply accumulate. Okay? And interestingly, so there's some more work that's been done. This is slightly different, but also I think very revealing from the group of Peter Abil at Berkeley, where they are breaking down the backpropagation into multiple blocks. In this case, the greedy learning corresponds to local losses that I just told you earlier, but you can also chunk these and as such. And what they find is that it's not in all cases. If you look at the cost versus the time necessary to achieve this, the Pareto front is generally not, does not include backpropagation, which is the blue curve here. So there are cases where these approximate methods of breaking the spatial credit assignment can actually help you, especially if you're looking at the cost and the energetic cost of the training. Okay, now this is just very anecdotal since I published this a few already we did the experiment some time ago. We implemented these ideas of the temporal and the spatial credit assignments for training spiking neural networks in spiking convolutional neural networks, just to show that these actually work. So here we trained this spiking convolutional neural network using a tool that's pretty much like SNN torch, and we achieved really good results on this DVS gestures task. And all of this training was online and using spikes, and they could be implemented as a synaptic plasticity processor on a chip. These particular results were obtained on the GPU just because at that point we didn't have neuromorphic hardware that could implement our learning rule. Okay. So now comes the slide where I'm trying to convince you that if you're thinking about doing learning on neuromorphic hardware, either on-chip, especially on-chip, but also off-chip, why you should use gradient-based learning, why you should use these surrogate gradient methods. So firstly, if you apply gradient descent to your spiking neural network training problem, this leads to a plasticity rule that's actually very compatible with neurobiology. These are sometimes called three-factor rules. And the reason they're called three-factor rules is that the learning rule here, I've written here explicitly the indices I and J for postsynaptic and presynaptic, so output and input. This learning rule results in one term which depends on I, which is the output, the output or the postsynaptic neuron, and two terms which depend one on the postsynaptic and one on the presynaptic. Okay, so this term here, which is also equivalent to this one, is like a unweighted trace of the inputs. So it's called, in this case, the presynaptic trace. And this here is the nonlinear function of the postsynaptic neuron. And you can see this as a form of Hebbian learning since it combines activities from the presynaptic and postsynaptic term. And this additional term, leading term here, which is the third factor, is some modulation, which depending on the problem, may depend on some global information. So this is information that you need to bring into the network in order to calculate the weight update. And this, from a hardware perspective, and please bear with me, I'll be really jumping from neuroscience to hardware here. This leads to a very interesting implementation of learning rules. You might, so in Hebbian learning or in spike time dependent plasticity, SDP learning, the errors, the updates are triggered on presynaptic events or on postsynaptic events. And if you go through this gradient descent, you just wonder, why is that the case? In fact, it doesn't really make much sense to do this. It makes much more sense to trigger the events, so to make updates based on errors. And if you can represent this modulation term as spike events, which is pretty possible, you can imagine that there's another piece of network that's computing the error and transmitting these as spike trains to a given neuron. Then error is communicated or computed in an event-based fashion. In this case, you can make the updates as soon as you receive that error. So instead of having spike time dependent plasticity, you have error dependent plasticity. And the result of this is that you need to make much fewer updates to your network compared to say using a plain gradient descent or say a CDP. Okay, so we did this work in fact with Melika. For the skeptics out there, I would still recommend to look into gradient descent because gradient descent is actually composable with other learning approaches as well, right? So say in the same way that when we looked at this these different modes of auto differentiation, so we saw that the learning is a composition, is a multiplication of Jacobians. Well, you can just truncate that computation just a couple of Jacobians. In other words, you can assume that you calculate the errors for these neurons, or in this term here, using methods that are not gradient based, but that target is achieved at the neuron using a gradient-based method. So this is what I mean that gradient descent is composable with other learning approaches. If you like evolutionary learning, heuristic, other stochastic approaches, it's perfectly compatible also with the gradient descent learning at the neuron or at the synaptic level. It enables higher order methods as well. If you can take gradients, you can also take gradients of higher orders. And so this is the case of, and Tim would be, Liu, one of my students, will be talking about how he uses the second order gradients in order to to optimize the quantization in the network from layer to layer. Okay, I think so. Melika, can you brief me on time?
Yes, so you are almost out of time, actually.
Okay.
So
I'll go very quickly
like
with
10 minutes, actually. You have 10 minutes.
Okay, but yeah, there's also time for discussion, yeah. Okay, my fault because the computer issues, I guess. Okay, so I'd really like to go briefly through this, which is learning online is very challenging, whether you do this on neuromorphic hardware or not. And that's because as we experience the world online, data occurs in a very correlated fashion. So it's not IID, and this leads to catastrophic forgetting. In addition to this, neural network models and gradient descent is inherently data inefficient. It gets worse if we're operating the real world. We're only at batch size 1. So this is a problem that reinforcement learners try to tackle. Labeled learning is generally unsuitable. We can use unsupervised methods. And so the end, we have non-idealities on hardware. So it looks like this is a pretty bleak future actually for neuromorphic hardware and learning if you look at these. There are some solutions. None of them have been fully developed yet, although we're working on one of them, as I'll tell you, which is we can have neurons that have synapses that have more so complex synapses, multiple states, as well as a replay mechanism that makes the data more IID. All of these methods are band-aids at best, by the way. So I'd like to talk to you about meta learning, which is a method by which you train a network for learning. So you learn to learn. And this is basically a more fancy and more systematic way of doing transfer learning. So on a batch of tasks, you can train the network to perform well on a class of tasks. So I'm going to quickly skip this, which is the work that Kenneth did. We implemented that transfer learning on the Intel OEE. I'd like to jump into this last result that I think is really important for the field in general. So there's one meta-learning algorithm called model agnostic meta-learning, which is very attractive by the fact that it's agnostic to the model that's being used so far that it's differentiable, or in the best cases, 2 times differentiable. It turns out the surrogate gradient, so this trick of using this continuous function instead of the step function, is a differentiable and twice differentiable function. So we can use this technique. And this technique corresponds to the following. it's an optimization of the optimization, right? So you try to learn an initialization of the parameters. You optimize the initialization of the parameters through the training loop, okay? And this is called the outer loop and the inner loop. I'm not going to go into the details here due to the lack of time. But the advantage here is that we can plug in our the same models that we use for training spiking neural networks and meta train the network. This is very good for doing few-shot learning, so learning very quickly. And this is why I had this picture of the tufa here again, because we're really approaching this idea of learning just on a single shot. What this requires is a family of tasks, say the recognition of digits or the recognition of images, and learning not only one task, but across multiple tasks by taking the gradients of the gradients. Okay, for this we have, of course, because we're doing spiking neural networks, we need to build a family of tasks. We did this using a clever combination of existing event-based data sets, so double NMNIS and double American Sign Language recorded with the TVS. And we were able to achieve the same results as we have with artificial neural networks. So just to quickly summarize this slide, so what we're doing here is a one-shot learning. So we're showing one sequence, one spike train corresponding to these two combinations of images. We're trying to classify 1 out of 5 different classes. And after a single shot, we obtain so nearly 99 and 97.5% accuracy. So the result of this is that you can very easily use meta learning to train surrogate gradients and 3-factor rules, which is by itself, I think it was really surprising that we actually even got this to work. And now this is the slide that says, why should you do this? And the benefits of meta training. Firstly, it's algorithmic simplicity. You're pushing all the difficult part of finding a good initialization to your supercomputer or your power-hungry GPU. And the part where you actually need to do the learning online for adapting to a new task is very simple. In fact, it's just a pure gradient descent update. Okay, it's not Atom or whatsoever. So it's very easy to implement in hardware. Low storage requirements. Won't go to the numbers here, but basically few very large updates are all you need in order to perform well on these tasks. You don't need much endurance requirement, right? So if you have devices, for example, that cannot endure millions of updates, this is fine because in this case, this particular neural network was trained with a single weight update to achieve that result. And finally, if you're in the field of memristors, you might know that memristors themselves don't behave in ways that we like to. They're not always linear in their potentiation and depotentiation or a set and reset. And so there's a lot of nonlinearity there. And something that we're exploring right now, which is very promising, is that we can take that nonlinearity into account in our meta learning algorithm. We can, for example, ask our colleagues who work on building compact models for memristors, which often turn out to be differentiable, and we can differentiate through that nonlinearity, such that the network finds an initialization that is unaffected by the nonlinearity or the asymmetry. Okay, so summarizing my slides here. Sorry for the delays. So we looked at gradient-based learning and the advantages of doing gradient-based learning. Meta learning, which is a way of training learning neuromorphic hardware for learning. And it's solving the problem that learning in the real world and on chip is difficult, and deep neural networks is not but the approach of training deep neural networks is not suitable for on-chip training. So the method of using meta learning can solve that problem. Okay, just quick acknowledgements to the funders and my collaborators. And so as Melika mentioned, so I just recently moved to Forschungszentrum Jülich, and my shameless plug here is that we are actually searching for several people to fill in the two institutes, mine, which is going to be on neuromorphic software and algorithms, and my colleague, Jean-Paul Strakan, who will be working on neuromorphic hardware nodes. Okay.
All right, great. Yes, that sounds great. You should get in touch with Emre. This is a really great opportunity. Do we have questions? We have maybe 5 minutes before we go on a break, so we can have a little bit of discussion. Maybe I can start until the questions are coming up. So one, I mean, first of all, thank you so much for the great talk, as always. One reason for using, let's say, online learning is that, you know, we have a really non-ideal hardware usually. So if you're dealing especially with analog hardware, you either have devices that have a lot of variability in time and in space, and you also have, if you have even CMOS analog devices, they have the same problem. And one of the, let's say, uses of using online learning is that this kind of feedback will correct the network to do what it's supposed to do, regardless of the mismatch and a noise that you have over time. Do you think that basically this type of meta learning approach and doing a few shot learning is going to still have that benefit, or you
For sure. And for the simple sense that you can meta train a network to be robust to you know, the hardware variations that you might occur, even if these occur over time. For example, if your devices are drifting, every time you read them, the conductance is changing. You can, in principle, meta train the network to be robust to that drift. Okay, so this is not hasn't been tested, of course, but the agnostic nature of MAML actually will allow you to do this. Will it work? You know, that's another question, because of just the computations involved may be a little bit too too big to run tractably. But yeah, for sure, I definitely do. That's exactly the kind of cases where I see a use case of meta learning.
Okay, but so even if this, let's say, change over time is completely random.
Well, so what you would do there, right, is you would try to find, that's what we would say if we discuss in the lab, say, oh, let's try to find a network architecture or an initialization such that it's not affected by that stochasticity. And and I didn't test this, right? So, but my guess is that if you build that kind of stochasticity into the meta learning, so the inner loop, it will actually find, it will exactly find that type of initialization. Without handcrafting, it would do it automatically for you. Yeah.
Super cool, exciting. Are there any more questions? Katie wants to ask a question.
Yeah, I have a question. Yeah, great talk, Emre. Thanks so much for presenting. So you just mentioned finding the right network architectures, network topologies. Can you comment on how you're using, or any particular approach you're using to find the right topologies for the algorithms you're developing?
Right. So this is something that you can't easily do. Right, so finding the architecture, you can do it in the sense that you can build in switches in the network, right? So you can gate the network for doing this, but there's no trick in actually searching for the architecture systematically here. It's not that I'm aware of. I mean, that said, so this model agnostic meta learning is not the only way of doing learning to learn, right? So it's in this case, we have this combination of outer loop and inner loop, But you can also imagine that the outer loop is an evolutionary or stochastic search, in which case it makes more sense there maybe to search for different architectures. This particular solution with model-agnostic meta-learning made sense because we have a differentiable spiky neural network anyway. So it was literally no cost, very easily to go from first order gradients to second order gradients.
Thank you.